people from India and Asia Pacific. Good afternoon, people from Europe and Africa, and good morning to people from US and Canada. Welcome to our webinar on solid state transformers and its applications in high power renewable energy systems. Our speaker for today is Dr. Harish Krishnamurthy from University of Houston. I welcome our chapter chair, Dr. Bijuna Kunj, for introducing the speaker. Ma'am, please.
Yeah, good day to all the participants. A very hearty welcome to all of you to the yet another webinar for our powers. We have been trying to arrange webinars for you from various aspects of renewable energy as well as electrical applications of using power electronics and even in the industrial applications also. We look forward for bringing to you the experts who are vibrant in doing the research and who can actually explain the versatile nature and the very minute things that they do in the research, which will always be an eye opener to all of you. And this time again, we have such a great gentleman who's going to present to you about the solid state power transformers. Uh, our Professor Harish is a graduate from NIT Trichy, and then he turned over to the one of the most prestigious institutions at Texas A&M, and he's currently the professor at University of Houston. In fact, I'm really proud to welcome Harish to this webinar.
Thank you.
We have been hearing the solid state power transformers, and I can very well tell you that I've been tracking the development of the solid state transformer research in currently that happens in even NIT Calicut also with Ashok sir. We have seen that all those designs, certainly there is something missing and which limits its application to using this smaller and efficient systems to the practical power electronic applications when we have the converters, when we have our PV cells, and when we try to interconnect, people don't try to put the power electronic transformers in between them also. There is some, a myth that they don't want to include. We hope that this myth will go and we will get a clear knowledge of what is being done in the new design that you have been doing the research with, and hope that our students and our researchers, those who are really interested in all these, who will take the information and will continue with further research in our country also. And we of course ask you also to collaborate with people here and continue with this research, and hope that we get more and more opportunity to work together. Welcome Harish, and welcome all the participants. Thank you.
So thank you very much for a very kind introduction, and then you were spot on in identifying the challenges in solid state transformers. So let me kind of begin with saying, basically my hometown is actually Thiruvananthapuram in Kerala. So basically this webinar is a virtual homecoming for me. So I'm glad to be here today. And today's topic is, basically my research so far has been kind of dominated by solid state transformers for multiple applications. And then here I thought, it will be good to highlight it with respect to renewable energy. So typically, solid state transformers, by the term, we usually intend, like any transformers with solid state devices. But now the definition has been a little vague, considering all this like EV charging application and all. You have high frequency transformers and so forth. So here, let me kind of rephrase a little bit for the purpose of today's talk. So when I say solid state transformers, it will be more for high power applications, especially to replace where conventionally people use line frequency 50 hertz or 60 hertz transformers. Then how do we replace that in high power applications like above 500 kVA to above 1 MVA? So with that, I'll begin my talk today. So just for bandwidth purposes, I'll close my video now and then reopen it once the presentation is over. So let's begin. So basically, I want to kind of start with a brief introduction to University of Houston. Then we'll give you a little bit background of transformers and higher power applications, power density, and then we'll talk about solid state transformers. Then we'll go to some of the renewable energy applications of solid state transformers, and then this is where kind of basically what comes in based on the initial discussion that we had on basically why is it not yet there in the market, and what do we need to do as a society collectively to improve that. So that will be highlighted in the last two sections. And so are you all able to see the cursor?
Yes, sir.
Okay, great. So that'll be good. So let me just begin with University of Houston. So University of Houston is a public university, one among the three largest systems in the state of Texas in the U.S. Basically, there are over 46,000 students in total. That's including undergraduates in multiple areas. And then in the College of Engineering alone, we have over $30 million annual research expenditure that comes out to be about 220 crore rupees or something in today. I haven't seen today what is the dollar conversion rate. So basically, we are in the city of Houston, which is considered an energy capital. Some people call it the world, at least like in the US. There are a lot of energy related activities going on in Houston. So a lot of the headquarters of several large oil companies and energy companies are here. So that's a brief introduction to the university. And specifically, I belong to a group which is like power electronics, energy storage, microgrids, and subsea electrical consortium. So we are one of the few universities who have research going on in the field of subsea and downhole oil and gas as well, considering our proximity to the energy industry. And we are heavily investing in 5G power conversion, radar systems, and using wide bandgap power devices. So here's a list of courses that we offer for graduate education, basically for masters and PhD. So we have 2 certificate programs, and we have master's degree, which is also offered completely online. So far, this online, it was basically like you had to be in the US to take it online. But this year, I'm not sure, maybe things might change because of the coronavirus situation. So we do have, our entire degree in power and energy systems can be taken online. And then basically, one good thing with I mean, of course, apart from this coronavirus thing, the one good thing which many universities in the US and also our university did is that we have GRE score waived until spring 2021. So in case if any of you are interested in pursuing your master's or PhD, and then if you haven't taken a GRE, again, this year is probably a very good year. So if you have any more questions with regards to this or even the technical topics, we can kind of discuss more towards the end. So let me kind of begin with a brief background of transformers and power density. So like I mentioned, our talk will be primarily on the higher power transformers. So primarily we need it for galvanic isolation, then step up and step down. So the step up and step down is what actually defined the main purpose of transformers, because basically that made long distance transmission possible, right? Because basically like you didn't want a lot of loss in the transmission lines. So once we were able to step the voltage up to a high voltage, that actually enabled long distance transmission. So transformers have played a very, very big role so far in the electrical industry. And traditional transformers last very long, 40 plus years with not too much of maintenance. So basically like, they may overrun our lifetimes, right? Then basically like, in terms of power flow, traditional transformers, they depending on the load and source, the power flow actually automatically happens. So basically like, traditionally there were like generations of stations. Then we were trying to kind of deliver power to the respective households or commercial locations. And then for that, traditional transformers were working great. And even now they are working very well. But there are some issues which we have to highlight before we go to today's topic. So one is, traditional 60 hertz or 50 hertz transformers are very large. Like if you go and look at a substation, most likely you'll see that the transformer is the largest component. If you go to a wind turbine application, you'll see that usually the transformer is the largest component there. So that weight and volume with an increasingly crowded space where that becomes more and more challenging. And then another aspect is now with aspects of let's say offshore wind turbine, and let's say if you want to keep a transformer at the top of a wind turbine or very close to let's say a PV system and so forth, what happens is that then the space becomes even more important. Let's say if we have a large area, then we don't necessarily care about the space much. But now, let's say not just for installation purposes, but the transportation. So if you have to transport transformers for certain applications, you will have to carry this entire weight for a very long time. It's going to cause mobility issues as well. So those are some of the issues with traditional transformers right now. And so they do not participate in active fault handling. So that is an increasing requirement now with so many, and it is expected that in the near future, almost 80 to 85% of electrons generated will flow through a power electronics converter. So when that happens, then there is a scope for a lot of faults in some remote locations, and also with increasing weather activity, there may be other faults happening. So traditional transformers, of course, their winding inductances and so forth, they help to kind of minimize the short circuit current to a certain extent, but they do not actively participate in fault handling otherwise, right? So because they don't have any active devices. Now, third part is again a very important part considering renewable energy applications, because they cannot regulate power flow. So you cannot use them to decide where the power will flow. So like I said, traditionally that was okay, considering there were the sources and then the load centers were all distributed, and then it was okay to kind of transfer power from one direction to the other. But now increasingly there are a lot of these renewable energy sources. People are installing it in their residence locations and so forth. So what if at some time the renewable energy generation on at the residential loads actually becomes more? So you have to be able to actively regulate the power in such cases. So far, like, though we were kind of happy with conventional transformers for several applications, again, that's a very critical point, right? Like basically we don't want to use solid state transformers for everything. For many applications, even line frequency transformers will be okay. But then for many other applications in the upcoming industry, the transformers are simply not smart enough for our liking. Now, there are some other terms which we'll be using interchangeably in this talk are power density. Basically, power density can be two things. One is power to volume density, and another is power to mass density. So most times, if you improve one, the other one will also improve. So you want to increase both to the maximum extent possible. Let's say if we are here in the total, like losses, cost, failure rate, volume, and so forth, we want to keep bringing this down and down until, if possible, we'll reach the apex some point when we have like an ideal system, right? So that's I mean, very unlikely, but that's where we all want to go. Now this, what are all the advantages of power density? We talked very briefly about that. So if you just take a look at, this is a drive. I mean, of course, it can be used in several applications, but this is a typical drive. You see this transformer. Obviously it occupies the most volume among all the other components, right? So of course this has some diode rectifiers and so forth. So basically this like if you're just considering a simple transformer itself, the size of this transformer is very large in volume, and then if you look at the weight, it will be almost 70% of the entire thing, because you see a lot of others are much lighter than the transformer. Transformer is very dense. So imagine if you have to take this to a remote location. Let's say in Texas, basically wind is very prevalent on the western part. So when it comes to the transportation, basically, like, you have to take this entire thing for a very long time. So it actually causes a lot of transportation fuel usage. Now, and even like in terms of installation, if let's say considering an offshore wind turbine installation, so you have to transport these transformers for very long distances offshore. And all these kind of add to complexity, and even installation maintenance will become more. And then if we are able to improve the power density, it will also reduce the overall cost, like considering all the three above. So the cost also can be saved, not just in the materials. So we have an analysis later on. So not just the material, but it will help reducing the overall cost. So this is just a quick example, right? So if you consider, let's say, a scale down 10 kilowatt inverter system. So like the EMI filter is roughly, let's say, 2.5 liters. The DC bus capacitor, say 0.5 liters, heat sink 0.5 liters. For this application, the transformer, if it is a line frequency transformer, 50 hertz or 60 hertz or something like that, that will be almost 14 liters, which is greater than 70% of the volume. And then most likely even more than that in terms of weight. So with that, basically so that's the main pitch, what everyone wants to go towards solid state transformers, at least where they make sense. So how do they make sense? That we'll come a little bit later. So before that, let's see what actually we can do, and then what is actually the reason for the large size of the conventional line frequency transformer, and then how can we improve the power density going forward. So this is the very basic Faraday's law. The actual practical equations may be even more complicated, but this one is very much easier to comprehend. So let's say for a certain RMS voltage on the transformer, it depends on all these parameters: the frequency, the number of turns, the peak flux density, then the area of cross section of the core. So in a traditional application, let's say in India, the frequency is 50 hertz. So when F is low, naturally for the same voltage, we need to have a higher number of turns, or a larger cross-sectional area. The flux density, of course, we'll be talking about a little bit on how to update it, but we want to utilize the maximum as possible. So let's say if it is a silicon steel core, we may want to try and go towards 1.5 Tesla as much as possible, depending on the material. So that is limited by the core technology. But what we have room for is variation of A and then the primary number of turns. So when F is low, those are higher. So that's one of the reasons why the line frequency transformers are actually like larger. So now if we are able to somehow increase the frequency, then for the same primary voltage, we will be able to reduce any of these three parameters or a combination of these three parameters. So that's what is why I'm mentioning as a combination is, basically, like, we would want to just simply reduce N and A, because that will affect the size significantly, right? Let's say if there's a 10 times increase in F, we may be able to reduce the product of N primary and area 10 times for the same voltage. But that's not that straightforward, because if you increase the frequency, then there is another aspect, which is losses, core loss, which will increase. So we cannot simply, even though we increase the frequency, we cannot simply just work on N primary and area, but we have to also look at the flux density. So we'll come to that in a little bit. So now, as we just discussed, there is one more, a very big item, which is the reliability. So as we discussed, like conventional transformers can operate for 40 years, without much of a problem. But now once you start introducing power electronics devices, basically, because like how can we, okay, yeah, before that, let's let's understand how we will be able to implement this higher frequency transformer for an application which has 50 hertz, right? So because once you have a 50 hertz grid, how do we change that frequency? So that's where power electronics comes into picture. So we use power electronics to transition the frequency from, let's say, 50 or 60 hertz to a convenient higher frequency. It could be like, medium frequency where it is, let's say, 1000 hertz, or it could be much higher frequency, 10 kilohertz, 20 kilohertz, and so forth. So we'll look into that implication also a little bit in this lecture. So so we can use power electronics for transitioning the frequency from, let's say, 50 hertz to higher frequency, and from the higher frequency back to 50 hertz or DC or whatever we need for that application. But then what are all the implications there? Of course, weight, volume, and losses we have to optimize, because once we have more devices, then the losses will increase, and also even the core loss of the transformers may increase, but the weight and volume can be reduced. Cost, again, there is a comparison table which I'll show you towards the end. So cost, depending on the type of material that you use, it may reduce or increase. Reliability is most likely aspect. So far, in my understanding, basically, if you move from a just transformer, a core, and winding, and you are adding even a tiny bit of anything, that's always going to worsen the reliability. So this is a partial answer to one of the questions which was discussed at the beginning. Basically, this is the reason, like, the primary reason for solid state transformers not coming full-fledged in the market. There are some isolated instances and occasions where people are using, but then full-fledged for higher power, especially like maybe more than 1 MVA. So it hasn't come to the market. It's mainly because of the reliability. And then there are concerns about losses again, but then it's primarily the reliability. So you can see in this chart, it's a good one. So basically, if you use a silicon steel core itself, which we use for traditional 50 hertz transformer, then we can go up to about maybe 1.2 kilohertz. After that, the core loss per pound can be very high. So we have to go to a different magnetic material. So that's why you see a jump in this technology. So let's say if you go to a ferrite core, there are many other, like you can go for much higher frequencies and so forth. So we'll discuss more about that a little later. So we talked about power electronics being used. So what is that really doing? Especially like considering it's a Saturday, it's a great day for equations. So I thought I'll put this slide. So basically, so let's say if your grid has a sinusoidal waveform like this, we can denote it with a simple equation. Now, imagine that, like, I always like to first think of it from a mathematical standpoint before actually going to a physical circuit. Once we know what the math does, the circuit actually just replicates that, and we just have to find a way to do it. Most circuits can do it, right? So let's say if we multiply the sine wave with a square wave. So as you can see, like, plus 1 to minus 1. It's a typical square wave switching function. Then if you instant by instance multiply, then you get a waveform something like this on the output. So how do we know what are all the frequency components? So you may say that, oh, it has a 60 hertz or 50 hertz envelope, but does it really have that frequency? So let's evaluate. So let's say you take the Fourier series expansion of the square wave. So you can see that it has a frequency at square wave, and then every odd multiples of that square wave, as we all know. So when you multiply two, a sine and a cosine, basically you get multiple sine terms, right? Like basically sine A multiplied by sine cos B will be like, it will be, half sine A plus B and sine A minus B terms. So that's what you are seeing here. It's basically, the frequencies just get added and subtracted based on simple mathematical trigonometric identities. So as you see here in this frequency, if omega square wave is, let's say, 1000 hertz, and then this fundamental term is 50 hertz, the frequency here is actually going to be 1000 plus minus 50. That's going to be 950 or 1050. So you can see that you are able to simply apply a square wave switching and get a higher frequency. So in this case, like I'm using the term higher, not high, because there like high in general means like probably 10 to 20 kilohertz and so forth in this prospect. but then it's still higher than the conventional 50 hertz. So now if you just take the Fourier series of this waveform, like using a simulation tool, you will see that the equations exactly match. So before going to any application, depending on what input you have, what is the output you need, you will be able to just come up with a mathematical formulation, like come up with a switching function. In this case, it is a simple square wave, but come up with a switching function that can give you the necessary outcome. And then there will always be some way to actually get that switching function implemented on the power electronics. So how do we get that? Eventually, of course, that is also very important, right? Basically, math alone will not be enough. So how do we translate it into practical implementation? That's how we can, in this case, it's called an AC to AC converter. So there are multiple ways of achieving that. So here is one, and then let's discuss more in this slide. So traditionally, AC to AC converters, basically when you need AC to AC conversion, you need to have a 4-quadrant operation of the switches. So the regular switches that we have at high power, like IGBTs, IGCTs, and so forth, and even silicon carbide MOSFET. So they are all, they are not 4-quadrant devices, right? So we have to have these devices connected in anti-series like this, so that you will be able to translate the input voltage, like, even when it is positive or negative, you should be able to generate either positive or negative outcome. So otherwise, it won't be able to block the voltage or conduct the current accordingly. So this is a very straightforward implementation, but there are a lot of challenges in it. One is this type of anti-series, especially at higher power, they can cause a lot of spikes, because you always have, like, let's say this side where it mentions V out, that's actually usually a transformer which is connected. So when you have connected a transformer, there will be leakage inductances in the transformer, and if you are not careful with the switching of these devices, it will create large spikes. So how do we solve that? That is one big issue, right? So we have to consider that. The second one is basically the packaging itself. So traditionally, in so many applications, we use a H-bridge, something like this, which is very common, right? So this module of the ACC converter on the left. So this type of module is relatively difficult to manufacture, and then it has much smaller number of applications. So that's why, like, whenever possible, of course, there are still applications where we have to use this, but then wherever possible, we would want to avoid that. Then what else can we do? So we can use something called an indirect AC converter. So these two are indirect AC converters. So what do they do? The first part simply unfolds, unfolds the input AC. So let's say if the input AC is a sine wave, you get a pulsating DC. So this capacitor is just a coupling capacitor, very small. So you don't need a large energy storage. So basically here it will be like a pulsating DC voltage. And then this second converter will simply operate on the switching function, which we discussed, like the medium frequency square wave. So this way, actually, much of the spikes and noise issues can be solved. And then this is a more traditional packaging. So the only trouble in this is, because there are two sets of converters, like we have to kind of take care of the switching instances a little bit, because we have to get a very smooth performance of the voltage on the V out, as similar to what the ACAC conventional full bridge can give us. Now, in applications where we don't need bidirectional power flow, like for example, let's say even wind turbines, a lot of times you just want power flow from the wind turbine to the load side. Maybe there may be some auxiliary loads in the wind turbine, but otherwise you don't need bidirectional power flow. Like motor drives are another example. You don't need bidirectional power flow. So then we can simply replace the first bridge here with diodes, because diodes are much more robust, and then you are just operating it at 50 or 60 hertz. So diodes can be used. So these are very popular technologies, and we'll talk more about that. So now let's go to like the actual implementations of solid state transformers. So the solid state transformers were actually conceived much earlier, like in 1968 by Will McMurray. And then you see, you can now relate this waveform. How do we get this, right? So let's say for a AC input, here he was like envisioning like mechanical relays and then switching at higher speed than the input AC, and we can get this higher frequency. So solid state transformers by their concept is relatively older, like it's over 50 years now. So after that, basically, like, so many different configurations has come, and then we are almost at the point where there's like, configurations do not alone make any difference. So if someone comes up with just some new configuration without really addressing the core issues of let's say the size and or the cost and reliability, then there is not much of an importance. So because you see there are so many combinations. So what are all the primary aspects of it, right? So one is basically as we discussed before. So basically, if we have a pulsating DC bus on our intermediate DC bus, like as a full wave rectifier, so that doesn't need an energy storage. But some applications have been using stiff DC bus and still calling it a solid state transformer application. Some people dispute that it's more like a DC-DC converter, but then some people say that, oh, we are anyway replacing a line frequency transformer with solid state transformer. So I don't have a certain opinion in that, but here I'm actually listing all the options which people are evaluating. So the first one is three-phase AC-AC converter. Like this is a direct AC-AC converter. Here it is a direct AC-AC converter on the primary, but indirect AC-AC converter on the secondary. Here it is direct AC-AC converter on the primary, and secondary side, it is not just that it is indirect. You see this large electrolytic capacitor here. So basically this voltage is stiff, not pulsating as in this case. So here it's a stiff DC. So then you tend to kind of, you can have this as a three-phase inverter, just like a typical inverter. So there is nothing much changing there. So there are multiple combinations like this. I don't want to go through everything. And then finally, it is like, basically you use a PWM rectifier and then just an isolated DC-DC and then another inverter. So basically this has much larger electrolytic capacitor right here. So that is a configuration which at this time it is kind of I would say more famous, considering it's a little easier to build, but of course it uses this electrolytic capacitor, and depending on the application it may either be large or small. So here if it is a three-phase, it may be still manageable, but if you have a single phase system, then those electrolytic capacitors will be much larger. So this figure shows you, so the figures here actually show you the expansion of what we discussed. So you can see how a three-phase to single-phase AC to AC converter can be designed. This is a matrix converter. Here it is a direct matrix converter and an indirect matrix converter on the secondary side. So here, again, direct matrix converter, and then here it is indirect, but with a strong DC bus, like a fixed DC bus. And then in this case, it is fixed DC bus on either side. So you can go through that. So I have given this link. So now again, like let's look into what all do the solid state transformers need to perform. So traditionally, like I said, people like transformers only had to do isolation, step up, step down, and then just take care of any issues coming, like not take care of, but then just handle anything that can come its way. So if it gets damaged by like lightning and all, just so be it, right? So but what happens when you have additional switches? So once you have a few more resources, people want to be more greedy. And in the right sense, so that power engineers can have more jobs, right? So basically, like now the solid state transformers are expected to take care of voltage harmonics, sag, swell compensation, outage compensation, maybe load, low voltage right through, load voltage regulation. You can see this entire thing. I don't want to go through each and everything, but so basically, you are expected to do a lot more with solid state transformers, considering there are more a number of devices. So basically, like you have to kind of take care of all the different things, whatever we can think of. So because of that, again, there is this concept of energy internet. what this energy internet it means is basically, every major port like this, people want to interface that to a solid state transformer. So with that in mind, basically, on the 400 volt DC side or whatever, like, 120 volt AC. So you may have a set of residential or commercial loads. You may have renewable energy connected. So basically this solid state transformer at multiple locations will act like, like an internet provider type of thing, right? So basically it will kind of regulate whatever is needed on the main grid, and then it takes care of any issues at this point. So this is a concept being flowed for a long time now. You can see this is 2008, and some places like the naval ships in the US, they are trying to adopt something like this for improved resiliency and safety of their ships. So it is getting to be more realistic, but there's still a long way to go. Again, because now the reliability itself of the solid state transformer and then the losses in the system, who will pay for it, right? Ultimately everything comes down to the cost. So basically, if the solid state transformer is only 97% efficient, if it was just a simple line or an inverter, it would have been like 98 or 99% efficiency. So you have to think about all those in perspective. So the first or one of the first, I would say, major breakthroughs in higher power solid state transformers was through GE. As you see, like, you can see when I was talking about this pulsating DC bus, you can see the shape of that DC bus here, right? So you have this AC input. You can use this, combination, like, here it is a high voltage. That's why they are using a series stacked IGBT or yeah, I think this IGBT switches. And then this DC bus is a pulsating DC. This high voltage silicon carbide devices will simply invert this pulsating DC to the shape that we were discussing earlier, and then secondary side something similar. So they implemented this, and it was very good. Like, people really appreciated it, and they even built a model. This is 500 kVA each, like the 60 hertz transformer, as you can see, and then this is the total solid state transformer for 1 MVA. Now, if you look at the transformer itself, like, that's actually a 20 kilohertz solid state transformer. So 20 kilohertz transformer. That high frequency transformer, you see that it's so tiny. I hope you are able to follow my cursor. So the transformers themselves for 250 kVA are so tiny, but there is a obvious issue. Again, this relates to what is practically possible, right? So here, of course, in terms of weight, definitely the solid state transformer will be lighter, as you can just guess from the figures. But in terms of volume, I don't see a big difference, right? Why is that so? Because since they were trying to operate at very high switching frequencies and high voltages, there were a lot of issues and fault handling capabilities which were needed to take care of all the power electronics here. So a lot of these are relays and breakers and all those, because you don't want your power electronics to break up. So even though the high frequency transformer themselves were very small, the solid state devices and the protection, everything added together, the cooling and everything added together, the system actually became much larger. So are we really getting the benefit of volume as much as intended, or can we take an alternate route? Do we need to complicate it this much, right? Because let's say this type of an undertaking requires very good expertise in manufacturing. So traditional transformer, it's already established, like, they can be assembled by technicians and others. But then for solid state transformers, like, you don't want to always have PhDs to build these transformers, right? So that's not how the world or economy for market goes about. So we will come back to that issue and then talk a little bit more, and then initially, like, let's kind of discuss some of the applications of solid state transformers in renewable energy. So here, what you see is a traditional medium voltage solar PV plant. Let's say I haven't gone through the actual circuit layout of the PV plant in Cochin International Airport, but I'm assuming it will be something similar, because let's say I think that power plant is somewhere more than 10 megawatts, if I understand right. So for such applications, basically what you do is you connect several solar PVs panels in series and parallel, and then you use an DC to DC converter, and then you have an inverter, and then you connect to a line frequency transformer and then interface to the grid, depending on what voltage you need. So this is kind of assuming a US electricity grid 13.2, 13.8. So in India, it may be a little different. So basically, you have several of them, because each inverter in the market are available. I think now it may be about 2 megawatts or maybe slightly higher. So you definitely need more number of such systems to connect together. So this is the more traditional approach. But again, if you are connecting this, let's say on top of buildings, or in a place where the size is very critical, then basically you don't want to have line frequency transformers. So here is an approach that we had published before. So what we did was, instead of parallel connecting everything at the AC side, so you see there is the solid state transformer here. You can see that there is an AC converter on the right side, and then you have here it was assuming that eventually we wanted to give a provision where, let's say, some of these panels can be replaced by battery. So in that case, we needed bidirectional power flow. That's why we use this AC converter. But otherwise, we can simply use like a diode and a H bridge, as we discussed before. So this solid state transformer, it's operating at medium frequency, I think about 600 hertz or something. So the size of the transformer could be significantly reduced, because this is very large power application. And then for high voltage, what do we do, right? Because there is one aspect of high frequency transformers, like you don't want the corona losses to be high. I mean, I think it's a term which we shouldn't use at this time, but the corona losses can be high when you have a large turns ratio from primary to secondary. So I'm assuming that, for medium frequency transformers, maybe 1 to 5 turns ratio may be okay, but you don't want to go much higher. For high frequency transformers, you want to be even smaller than that. So so because of that, like basically we series stacked the different converters like this, and then eventually got a 13.2 kV AC. So of course we implemented in a scale down lab prototype. But this concept, again, there are some aspects of the voltage balancing, which again we published in another paper. But then, considering this as talk on solid state transformers, I don't want to go to the control side. But yeah, so basically we can actually, instead of this application, we can actually move the transformer to the earlier stage, and then just series connect or parallel connect the inverters accordingly. So that's another option which you can try for solar PV applications. Now, again, there are different combinations of solar PV applications which will be there, but they all follow the same theory. So if there are more questions, I can address a little later. But again, one thing we have to notice is that there is nothing much too complicated in the topology alone. Like if you're just seeing it's just a H bridge. So nowadays, like people want to stick to the simpler topology or configuration. People are like, so coming up with fancy circuits, it's not really a very attractive thing nowadays, because there have been so much of research already in several converter designs. But now optimizing overall as a system, that's very critical. So similarly, like on a wind farm, so this is a whether it is an offshore and onshore wind farm, basically they are kind of connected with AC terminals all together, and then they are brought to a transformer substation, and they can be kind of then they are either taken to the shore directly as high voltage AC. In some applications, they are connected as DC. But now the problem is that once you go offshore like this, these transformer substations and all those have to be somewhere on the platform deep inside the ocean. So what that does is, again, all the problems that we discussed before, you have to transport these transformers, like huge transformers, so far away into the ocean. And always, like if there is a problem later on, you have to kind of, maintaining and all those becomes a big problem itself. Because now it's not just the transformer, because the transformer is working together with power electronic devices in any case, right? So so what we did is, just for a land-based application probably, or there. So we came up with an solid state transformer based approach. Basically, like let's say if you have this, assuming a direct drive wind turbine, you can have a three-phase PWM rectifier and then a three-phase PWM inverter. This inverter, instead of giving a line frequency or 50 hertz, 60 hertz AC as is done in this case, because you directly want 50 to 60 hertz, here we can it's transitioned to a medium frequency. As you can see, this is the voltage that the transformer will see. So then you can use this AC converters on the other side to interface to the grid. So this way, your size of this particular transformer can actually be much smaller, as small so that you can actually take it and put it at the top of your wind turbine hub. So basically, all these wind turbines which are connected, rather than placing the transformers on a farm or on a platform on the ocean. So basically, you can actually take this and put it at the top of the wind turbine hub because it's much lighter. So in terms of weight, it will be even smaller, right? Because the core material is much smaller. So this is something which we have been looking at, and then this is a slightly different application, because like when we presented that work, basically people asked, basically, is there a way we can interface battery energy storage to such systems? Because considering there is a lot of issues with regulation of wind turbine electricity. Basically, if you combine with battery storage systems, which is increasingly becoming important, can we do it with a similar topology? Yes, we can. Basically, what we do is the primary side, if you just take the wind turbine, it is very similar to the one before. The difference is that now we have added another port for energy storage systems like this. So from this DC bus onto the other side, the way that the wind turbine converter operates, we just have to remove this three-phase PWM rectifier, and then the remaining aspects remain very similar. So depending on whether you need, if the demand is higher, then we can use this energy storage also to pump energy to the grid. So this actually shows you an example of a medium voltage grid. So you may need more series stacked AC converters. So that's this topology. So like I said, if you see here, once we understand the basics of the solid state transformer, all these concepts are very straightforward, considering it's just one AC converter on one side. Depending on whether you have an AC or DC, you use an inverter or again AC converter, and then you just combine it with the transformer. So it's a very straightforward approach. I always prefer square wave switching whenever possible. So of course here we can do square wave switching, but for the PWM rectifiers, we had to have a combination of square wave and square wave and sine PWM. So it was a combination of both. So you can read this paper to understand more like how that PWM modulation is taken care of. So like I said, since it is not directly relevant to the solid state transformer technology, I'm not going to too much detail in that. So what about offshore MVDC distribution? So as you see, for offshore applications, usually from wind turbine, once you create the DC bus, there is one offshore platform which actually converts this DC to a medium voltage DC. But so far, whatever people have been doing right now, like till this date, they have been using a conventional 50 to 60 hertz transformer here. Because again, it's something which people already know. Again, that's something which people have tried out before, so they just want to stick to it. But see, there is a big thing, right? Anyway, we are using this power electronics. So when we are using power electronics, even in this application, then there is a much more incentive actually to take this transformer and make it to a medium frequency. So basically, this that's another thing which we will see in this architecture. So basically what we presented here is to take this transformer to a medium frequency approach, and then directly generate the DC after the first transition. So here is the figure, which I'm talking about. So if you have an AC to AC converter, as we discussed before, this is a indirect AC converter, use a medium frequency transformer, and then you have a rectifier, and on the secondary side, you create a medium voltage DC, maybe plus minus 20 kV, and then this is for a single wind turbine. You will be able to place this at the top of the wind turbine itself because the transformer size is much smaller. So we can avoid this platform that you see here and take this converter on the wind turbine itself, so that this we may still need, but at least we can eliminate one complete platform. So it will make it much easier. So that's what we had proposed. I'll skip this because anyway, because of lack of time, I want to go into the design of the transformer itself. But this is another aspect of energy router. This work is from CPES in Virginia Tech and Office of Naval Research. So how much can we actually reduce the size of transformers, and how much more efficient and reliable can we make, and then what can we do, right? So these are the equations for the hysteresis and eddy current loss. So typically, the losses are a function of frequency and the flux density. Like whether it is eddy current loss or hysteresis loss, it's just the power may change a little bit. So if we increase the frequency, what's happening is the loss per pound is actually going to go high significantly, because it's a power of 3 over the power 1.5, right? So we have to do something if we are using the same core material. So let's say if we are using a 50 or 60 hertz transformer, if we want to still use the same silicon steel core, which is being used in conventional applications, then we have to find a way to reduce the flux density a little bit. Otherwise, the core losses are going to be significantly higher with the same material. What else can we do? We can go to better core materials like amorphous silicon core, which is very good. We can go with ferrite core, which is again getting popular. Like what GE used is a ferrite core. So ferrite core materials have much lower losses. But again, if we go for higher, they are valuable maybe once you go towards 10 kilohertz and higher, because otherwise you don't get much size benefit from ferrite core. But once you go to 10 kilohertz and higher, what happens is the power electronics switching losses will be significantly higher, right? So there needs to be a balance between those two. So what we can do is, even with the conventional silicon steel or amorphous core, we can either reduce the flux density, then we will be able to make the overall losses very similar. This table summarizes that. So instead of a 60 hertz, because I was working in the US then, so basically I'm using a 60 hertz as reference, and then move to a 600 hertz for my application, which is a medium frequency transformer. So we'll be able to achieve similar efficiency of just the transformer itself, but at, like you see the volume, right? The core volume is almost 1/3 of the 60 hertz transformer. So, but then there is one aspect which you will be thinking, what about the power electronics? So once we add the power electronics, this efficiency will come down to about 96.5 or something like that. But if you want to have a higher power electronics, higher overall efficiency, we can go to this amorphous silicon core transformer, which is still not very expensive, but still it's much more efficient than silicon steel. So I did a empirical cost analysis. So if you use a silicon steel core material, you can actually make the cost very low. Like you can see, if it is 1.4 per unit, you can make it almost 0.5 per unit. And even with power electronics, it will still be cheaper than that of the conventional line frequency transformer. Because see, why this is small? Because the core material can be significantly reduced. So the power electronics cost can be offset. But of course, with a lower loss, lower efficiency, slightly lower efficiency, right? So, but if you go to an amorphous silicon core, you may still be able to balance the cost of the conventional line frequency transformers at higher efficiency. So these are certain things to keep in mind. And then this is kind of the essence of why should we go to a high frequency, or can we limit at medium frequency? So we did an empirical comparison of, let's say, a converter, a system with an AC input and then a DC output, right? So for AC to AC conversion, things can be a little different. But many of the applications have either AC on one side, DC on the other side, and so forth. So that was one of the reasons why we chose that for comparison. So if the line frequency transformer based converter approach is 1 per unit. So as we saw, an example will be that wind turbine where we had converters on either side and then the transformer, right? So now if we use a medium frequency transformer, the overall size, considering the capacitors, heat sinks, EMI, everything put together, actually it will be almost, we'll get almost a 50% overall system volume reduction, which is a significant number, and maybe almost a 70% reduction in weight. If we go to a higher frequency transformer, this is a ferrite core material with 6 kilohertz frequency. So with a higher frequency core material, actually, if you look at, because we are switching at higher frequency, we need more cooling, we need better requirements of EMI filter and so forth. So in terms of size, of course, it is smaller than the medium frequency, obviously, but is it worth going to much more complicated design, as we saw earlier, right? So the design itself is so much more complicated because it's a higher frequency transformer. So is it worth going to high frequency for high power applications? I'm not very sure. So we have to look at that application more closely and decide whether should we go to a medium frequency or high frequency because of these reasons. So there are still challenges with EMI. I'll quickly kind of brush through it, and then if there are more questions, I can take it as along. So as you can see here, for AC converters, the losses of line frequency transformers, like it's just metal and conductors and core. So basically, it's almost impossible to beat the efficiency of traditional line frequency transformers because in terms of losses. But when it comes to an application, as I was just discussing, right, applications where you need an AC to DC conversion and so forth, then solid state transformers will come into picture because anyway you are using converters. If you are using a much smaller transformer, you can save a lot on your size as well, and then your solid state power devices efficiency can also kind of be improved by using wide bandgap devices and so forth. So here is the we have to kind of look into this. So if someone asks you, is solid state transformer good for all applications? Then the answer is it depends. It's not good for all applications for sure, but then we have to choose. So wherever space is a constraint, wherever typically let's say an application demands mobility and so forth, such places solid state transformers benefit heavily outweigh that of solid state transformers, traditional line frequency transformers. So in order to improve the reliability, again, like people are trying for better and better reliable power devices, but then there are research going on in health analytics and remaining useful life prediction. So we ourselves are working on a machine learning based prediction algorithm for solid state transformers and in general power converters. Again, like I said, that could be a topic for a completely different discussion, but I wanted to highlight as long as we are not able to completely achieve very high reliability for power converters, at least this way we will be able to monitor if there's a failure. So that is the best we can do at this time. But again, up to 15 to 20 years of life. So for example, with medium frequency transformer, I think we may be able to achieve almost 20 years of life. With high frequency, because considering there will be more stress on the devices, maybe we can look at somewhere around 15 years of life. So for such type of designs, we'll be good with solid state transformers already. And then again, these are some research areas which are being followed. Design optimization. People are trying to come up with this multi-objective design optimization to get the best size and best efficiency and so forth. So that's a very major area of research going on. And then another is design automation. So once you have this setup, like why do we need humans anymore to optimize? So once you have this entire thing, give the input specification, and then the automation algorithm will be able to completely give you the optimized solution that you need. Of course, this has to consider the heating, thermal modeling, and everything. Otherwise, your result may not be justified. So finally, I would want to kind of stop with this especially for renewable energy and large applications. People are increasingly going with this real-time simulation. So people you can have a digital system with real-time hardware in the loop circuit with the same controller hardware, but in this case, this is actually a practical, actual inverter system. Here it is actually modeled on a computer. So you'll be able to check the performance. And if there is any anomaly detected from the actual system with respect to its operation in the computer, people are trying to use that to predict the failure. And so such type of research is also going on. So with that, I want to conclude this talk. So basically, overall, with solid-state transformers, we can achieve a reduced footprint, improve controllability. To a certain extent, we can get fault isolation. So medium frequency transformers may be preferred for higher power applications. So until people have completely figured out, how to take care of all this high frequency switching with high frequency transformer operation for high power, it is probably better to go with maybe an amorphous core material and operate around 1 to 1.2 kilohertz. This way, you will get a very significant size reduction. At the same time, even conventional IGBTs at high power, several megawatt range, IGBTs can operate at that frequency without much issues, right? So if it is a square wave, it is very easy for IGBTs to switch. Now, again, we have to increasingly use health analytics and others. It's a data-driven approaches are taking much more precedence in multiple domains, not just solid-state transformers. So overall, we want solid-state transformers for a smaller, lighter power conversion, and I'm very confident that this technology is going to only be more popular going forward. So with that, I'll conclude my presentation, and thanks so much for listening. If you have any questions, I'll be happy to take them.
Thank you, Dr. Harish, for the very enlightening session on solid-state transformers. Now it's time for Q&A. We have some time limit, some time constraint, so anyway we can take a couple of questions. Eldo,
yes, sir.
question?
Yes, sir. We do have one or two questions out here.
Yeah.
Yes.
Let me read out. In slide number 20, why there are no filter capacitors in some topologies? How to select the DC link capacitors and AC link capacitors in the experimental setup?
Okay, great. So slide number 20. Good question. So, so here is the thing. So as I mentioned, can you see my? Okay, let me make it. Okay. So, so in this case, basically, whenever there is no capacitor, it just means that this link is supposed to be like a pulsating a DC link, or it's like a full wave rectifier waveform. So basically, if you have a weak DC link, so in this case, because it's a three-phase system, it is not going to be a full wave rectified waveform. It's going to be like a combination of, it'll almost look like a 6-pulse rectifier waveform, but it will be chopped, because this is actually a three-phase rectifier. So what will happen is that you can eliminate a capacitor right here. You may still need a very small capacitor, which will be in a few microfarads, just to decouple any high frequency noise. So here it is not intended that the capacitor smoothens the voltage. So basically you live with that chopped voltage, basically. So the capacitor is not there to smoothen. And then basically you use this converter and take whatever responsibility comes out from that noise. But in this figure, basically, once you have this DC capacitor bus, what happens is that the power flow from the AC side, this particular voltage is actually a stiff DC bus voltage. So it is not a chopped voltage. It's just like a typical inverter that you have. And how do you choose this capacitor? So this capacitance value you would choose by looking at the highest, or the lowest frequency term, the highest magnitude term or the lowest frequency term, depending on the particular application. So in this case, most likely it will be the switching frequency of this converter. Because it's a three-phase system, there won't be any second harmonic ripple. So you have to design this capacitor in such a way that the switching frequency current mainly passes through this capacitor and doesn't produce a lot of voltage pulsation of that frequency in this DC bus. So basically all you have to use is V equals I times Z, where Z equals 1 over omega C. In this case, omega will be depending on the switching frequency of this converter. I hope that answers your question.
Eldo? Eldo, next question, please.
Yes, sir. Sir, shall we wrap up things because it's around 9:05?
Yeah, you can read one more question, I think. Maybe
Okay.
maximum.
Okay, sir. Next question. Could you please share some links for working towards solid state transformer modeling and control?
So links for, okay. So basically, what I can do is I can share this presentation. So if you go to, let's say these type of links, which people have been, so you look at this IEEE link, right? So basically some people have been working in this modeling and design so this is design optimization and so forth. So I'll send you this presentation like just after this call. And then if you follow these links, you'll be able to get very good references.
Okay,
Okay,
thank you,
thank
Dr.
you, sir.
Harish.
Okay.
Eldo, now
Yes, sir.
the rest of the question can be sent to the mail ID of the speaker. So
Right.
he will
Yeah,
reply
it'll
to
be
the mail.
great if you can kind of, maybe let's say if there's a collection of these questions, I can answer everything at the stretch, and then I'll be happy to do that.
Okay.
Sure, sure.
Okay, we'll mail the question, sir.
Now I invite Dr. Vasanthi, Secretary of the chapter, for the formal vote of thanks. Vasanthi, miss, please. Vasanthi, miss, please unmute your mic. Hello, please unmute. Hello,
So
you are not
Miss
audible.
Vasanthi ma'am
Please.
here.
Yes, I think there are some problems.
Yeah,
So,
Vasanthi is not there.
so I request Bijana ma'am for the form.
Yeah, again, thank you very much, Dr. Harish. It was
Yeah.
quite eye-opening for many of our students also. Like, how can you go ahead and where is the point to be thought about? It's really good that you have given the links also so that they
Mhm.
can go and find out. Thank you very much for spending so much of time,
Sure.
putting so much of effort and sharing us so much of information. Thank you very much.
Yeah,
And
thank you.
looking
Thank you for
forward
inviting.
to further collaborations also.
Sure, absolutely. I'll be glad to. So thank you
Thank,
so much for
thank you
inviting,
very
and
much.
it was a pleasure to have this webinar today. Thank you so much.
Thank you to
Thank you,
all our
Harish.
students team who have been
Participants.
doing all these meticulous
Yes.
operations for those arrangements. Thanks to all the participants who actually listened to the whole webinar and got the complete information. Looking forward to your
And
support in the future also, with your presence and your membership also. Uh, thank you all. Thank you, Sridev, for making the arrangements. Thank you all.
bye.
Yeah,
Harish.
thank you. Yeah,
Goodbye.
And
bye.
Goodbye.
participants, please kindly fill the feedback form.
Thank you and good night. Good day. And Eid Mubarak for those who are having Eid tomorrow.